Hello guys, good morning. Can you all hear me? Could you please type yes in chat box if you can hear us? Thank you so much. I wish you all a happy new year and on behalf of HIW, thank you so much for your presence in the webinar. And we HIW is a training institute who train the electrical engineers basically on uh, electrical system design and also various concepts of design so that they learn an industrial oriented training and get placed in various companies. So today we are conducting our 14th webinar as a part of 100 webinars mission in the year 2021. And I would like to introduce Mr. Kashish, who is an 2-year experienced guy in electrical system studies, and he's working as an system study engineer at Vadodara, Gujarat. And he's also a member of Institute of Engineers in India, associate member of India. Hi, Kashish.
Yeah. Hello. Good morning.
Good morning, Kashish. Thank you, thank you. So you can continue, Kashish.
Yeah. Okay. Shall we start? So.
Sure, sure.
Yeah. Okay. Good morning to one and all present here in this digital platform, and happy New Year to all.
Good
As
morning,
this
sir.
is great. Yeah. Okay. It's a great initiative taken by Hyderabad Institute of Electrical Engineers that they are conducting such kind of sessions to train the upcoming engineers. So first of all, I would like to appreciate HIEE for this for giving me such kind of opportunity to conduct a webinar on relay coordination and to get aware the upcoming engineers or the engineers who are currently working as a power system in power system domain. So to get refresh, this webinar is been conducted. So now moving further, not taking much time, let's move further. As we all know that today's webinar is for relay coordination and using ETAP software. So the topics or the overview of the presentation will be the power system study, power system protection. What is power system protection? Actually, the field is. Then protection, why we need protection, what is the protection, and how we can protect our power system. So why, what, and how. The essential qualities of protection for giving to protect the equipments in power system, the relay coordination, relay setting calculation, the time current curve, characteristics curve, and with some example in ETAP. Okay. Hello, Bhavya ma'am. If my pace is very fast, then please let me know that I
Yes,
can
sir.
slow
Yes,
it down.
sir. Yeah, you have to slow a bit. Thank
Okay.
you.
Okay. Thank you. Yeah. Thank you. So, for power system protection, as we all know that day by day many industries are getting expansion are expanding then industries in terms of load, in terms of new units, or in what we can say. So for this expansion they need to expand the electrical network. So expanding electrical network, they need to install more transformers, they need more power from the grid, or they have to set up, or they have to establish their own in-house generation. We can say the captive power plant, CPP plant, or adding more branches in the network, adding more load. So in order to protect this equipment and to know the behavior, to know the performance of this electrical system, we all need to go with certain studies. So the power system protection is a branch of electrical power system which deals with the protection of electrical power system. So by giving protection, we can't prevent the fault, but we can minimize the consequences which occurs after the fault. So we can't prevent the damage occurs due to this fault, but we can control the damage in we can say in a count of amounts, that the damage should be minimized. The objective of protection scheme is to keep the power system stable by isolating only the components that are under the fault. Means, let's say if a particular feeder or particular equipment is if in particular equipment certain fault occurs, like we can say the short circuit occur in one motor. So only that motor feeder get isolated from the system. Not entire network should be interrupted. So power to the healthy system should be continued. So in order to isolate this system or to protect this equipment, the device that is used to protect for the to protect the power system from the fault are known as protective device. So protective device will be in terms of, we can say, circuit breaker, relays, isolators, insulators, which lightning arresters, etc. We can, and the terminology which we are using is the switch gear for this device. Moving ahead. So protection, why, what, and how we need to protect this equipment. The protection is means a good electrical system should be ensured that availability of power, electrical power, without interruption to every connected load. As power is transmitted to our network or to our premises through high voltage lines which are exposed to environment. Hence there are certain chances that the conductors can be break down, or there is a failure in the conductor due to some storm or falling of external object to the overhead line, or damage to the insulators, or any three phase gets short, or line to ground fault occurs which results in electrical fault. And this fault will convey to our network, and it will get disastrous fault will be at our premises, and the equipments connected to this load gets damaged. So in order to avoid this in order to avoid this condition, to avoid fault and to protect our system, we need to install protection relays. As relaying scheme detects the abnormal conditions like fault in the network, or and automatically operate and give the tripping command to the switch gears like circuit breakers to isolate the faulty part from the system as soon as possible, so that healthy system could be saved. And this will limit the damage of the fault location and prevent the effect of fault spreading in the system. So the switch gear installed all for this, it must be capable to interrupt the fault, and also it should be able to withstand during the normal running load. Okay. Yeah. So in order to safeguard the entire system, we need to and to maintain the continuity of the supply, we need to install the protection schemes to save the healthy system from the fault to get damage, or to get damage, and to minimize the damage associated with the equipments and repair cost. Means to even by installing this electric relays, or to by giving protection to the system, we can minimize the damage, and it will also save our equipments, and by the way, consequently we can say it saves our cost. The protection is also applied to give the safety to the person, or the one guy who is nearby the equipment. Yeah. So abnormal conditions or types of the faults. The fault can be classified into three types. The fault will be in terms of current, voltage, and frequency. So for current, we can say overload. This overload will be the abnormal condition. It will not be considered in a fault. Overcurrent means we can say in the abnormal condition. We cannot say it in a fault. The earth fault, it's actually a fault. Current unbalance, short circuit, like three phase fault, line to ground fault, double line to ground fault, double line fault will be considered as a short circuit fault. In terms of voltage, there are certain faults we can say in terms of voltage, like over voltage, under voltage, voltage unbalance, neutral shift. In terms of frequency, it will be over frequency, under frequency, and rate of change of frequency. That usually occurs from the grid end, and when there is a in-house generation or having a generator, then we can say this protection will become in the picture, that is rate of change of frequency, over frequency, under frequency. Now, essential qualities. The essential qualities for protections are speed, selectivity, sensitivity, reliability, simplicity, and economy. The speed means the fault should be isolated from the system as soon as possible, so that equipment can be saved from getting damaged, and we can save the system to get unstable. So we need to ensure that the switch gears which are installed all for the protection should operate in minimum time, so that our equipment gets damaged. The selectivity, the maximum continuity of service with minimum system interruption, means the switch gear which we are using for protections should be able to withstand the maximum amount of should be able to withstand maximum amount of current which equipment is rated for, such that in normal condition also the equipment would not operate or would not give a fault command to any another circuit breaker or any another switch gears. And also in simultaneously, it's also be able to interrupt the system in a minimum time or in a minimum amount of current, fault current, I can say fault current, so that the system could be saved from getting damaged. The sensitivity, to detect the system, to detect the smallest, even the smallest fault current or system abnormalities, and to operate the correct switch gears. Reliability, to assure the operation with which operate correctly, means if we are having the triple line fault, means short circuit condition, then the switch gear should operate for the short circuit condition only, not for any another protection. Simplicity, minimum protective equipments and associated circuitry to achieve the protection objects. Economy, provide maximum protection at minimum cost. So as we all have studied that in terms of economy, the protection part is only the 5% of entire electrical net substation. So the protection should be implemented in our system in such a way that it protects entire system with a minimum cost. So the cost of the protective systems should be balanced against the risk involved if protection is not sufficient and not enough redundancy. So the primary objective of the fault is to protect the particular zone to that it operates primarily first. But if some kind of protection gets failure, then we need to have some kind of backup, that we can say in a selectivity, such that it should operate if any switch gear gets malfunction, or if it didn't detect the fault in the network. Protection zone. As our substation is having numerous electrical equipments which are having the generators, transformers, bus, transmission lines, motors, even utilization equipments like motors, static loads, capacitors, or reactors. So in order to protect the entire system, we need to divide this substation into certain kind of zone, in a protective zone, such that it will operate for that reason only. And if that protection zone gets failed to detect the equipment, we need to have some backup protection. So such that this zone should be divided in such that it should provide primary protection as well as backup protection to its downstream network. Here in this figure you can see, the generator, transformer, bus protection is bus bar, the transmission line which is going for another substation or another bus, then another step up transformer, then this is a bus, and the utilization equipment means a motor. Now the protection starts from downstream. We can say that it should protect the motor first, then the bus, and the bus, its upstream bus, in such a way that bus should this protection should provide backup to this motor zone. It provides protection to the motor. Then this bus should be operate primarily, means this bus should isolate first when the fault occurs in this bus also only. Then a transformer zone, it should also provide a backup protection to this bus bar. Then this local fault protection, then another primary protection should be given to this transformer. Likewise, from downstream to upstream, we need to divide certain zones for protection equipment. As protection is a major concern in any industry, and the relay on the we should rely on the protective device for the same. So in order to ensure the protection, we are having some relays which sense the fault and give a tripping command to the circuit breakers associated with this relay, and this circuit breaker will trip the faulty network and isolate the faulty part, and such that the healthy system would be saved. A relay I think screen gets stuck. Hello.
It's visible, Kashish.
Okay. Thank you. Now let's move. Okay, this protection zone. Now we should, before going further for relay coordination, let's have some another basic idea from here only. As we are giving protections to every equipment, so it will be known as the unit protection for every equipment like motor, transformer, generator or line. It will be having a unit protection. But now as we are talking for the relay coordination, such that relay coordination should be done from the downstream to the upstream. That it's for down, you can say that the downstream, here you can say that the downstream will be this motor and the upstream will be this generator. So it should be the protection should be given in such a way that the relay or the protective device installed for this motor should operate first, and if this not gets operate, then its backup protection should operate. So in such a way, in this way only, we have to coordinate our entire network from downstream to upstream. And to coordinate this electrical network, we need to go for relay coordination. As we all are aware of relay coordination, that what the term, sorry, I will say the terminology, the coordination means to coordinate entire system from one level to its up level, from down level to up level. So in this way also in our electrical system, we need to protect our equipments. We have to coordinate our electrical system from downstream to upstream. So let's go for relay coordination. The relay coordination, the term relay is the automatic device which sense the abnormal condition in electrical system, and it's give a tripping command or a signal to the circuit breakers associated with this relay. The protective relay should be the protective relays are having functions like it measures the current, voltage, frequencies, temperatures, and with this measurement it gives the tripping command, or it gives a tripping command to the circuit breaker. The protective relays are having certain inputs, this current, frequency, and voltage, as I said. Now we can set the protection settings, like for over current protection, for short circuit fault protection, under voltage, over voltage philosophy, over frequency, under frequency philosophy. We need to provide some protective settings such that if any quantity, let current or voltage, goes beyond this the set parameter, then it should pick up and it should give it should raise a tripping command to the, and it should raise a alarm as well as a tripping command, such that we can get to know that the system gets faulty or abnormal condition has been raised in the network, and we should take certain necessary actions and give a tripping commands to these breakers associated with this relay, and it should isolate the faulty feeders, and we can save the healthy system. So here in this figure, you can see certain flow block diagram, which has been showing that this protective relay is a simply, we can say, a device which detects the current, voltage, and frequency. Also, it will also detect the temperature uh, for for thermal overload or transformer. We can say that for transformer uh, protection, we are having source protections. So these numerical relays have features which can detect, which can sense the current, voltage, and frequency. So with this measurement of current, voltage, and frequency, the relay will shows the certain measurements of these quantities. Along with this, we can set this relay with certain protection settings, such that, like, we can say the pickup value of the current, voltage, and frequency in such a way to prevent our system from to gets damaged from fault condition. The measurement and the protection settings which we have given to this relay will be this will compare with this relay, and if any value goes beyond this pickup value, then it will raise the tripping command and isolate the feeder. Moving further, as I said, the system or equipment should be able to the system or the equipment should be able to discriminate the appropriately, and should disconnect the feeder and should disconnect the switch gears associated with this feeder at which the fault occurs. The relay coordination is a study that ensures the tripping of protecting relay in a sequence or a proper order in electrical system. As I said, relay coordination is done to isolate the faulty part and to minimize the faulty condition, and to minimize the faulty condition. And this for relay coordination should be done in such a way that it should isolate the fault with the minimum time of operation of relay and a circuit breaker. With the help of relay coordination, we can determine the protection settings of the protective equipments for overcurrent condition, for for voltage also, for over voltage and under voltage conditions also. With this relay coordination, we can ensure that faulty parts get isolated in a speedy manner, and the selective and reliable operations should be ensured while for the normal conditions also. As we can say that during normal condition, this protective relay should be able to withstand the normal condition, and it should able to detect the faulty condition, such that normal condition should not be interrupted and it should not be isolated, and it should not detect this condition as a faulty. The relay coordination should be done in such a way to avoid the nuisance tripping in the plant, and thus to enabling continued service in a healthy part of the network. So let's move further. Relay coordination. Here you can get a better idea for this relay coordination, what actually the term relay coordination is. Here you can see typical diagram that the main bus is feeding to the network, and there are certain outgoing feeders going to the certain locations. Now, the term relay coordination means if any fault occurs in the first feeder, then the circuit breaker associated with this feeder should isolate, not the incomer feeder should gets operated. If this incomer feeder will operate, then there will be a blackout condition occurs in the network, and the healthy feeders also will the power to the healthy feeder will also interrupted. So the coordination should be done in such a way that the feeder at which fault occurs should only isolate, not its adjacent feeder or its incomer feeder should isolate. The figure A on the left hand side of your screen, you can see that the miscoordination of the network. It means fault occurred in the feeder number 1, but the incomer feeder gets operate the circuit breaker associated with the incomer feeder operate first. So this leads to the blackout condition to the other outgoing feeders. The power is interpreted to other outgoing feeders also. So this is not a proper power supply scheme or protection scheme. So in order to have proper coordination of the network, the coordination should be done in such a way that the feeder, you can see the figure on the right hand side of your screen, that the feeder 1, there is a fault in a feeder 1, the circuit breaker associated with this feeder only gets isolated. If somehow due to some reason this circuit breaker unable to detect this fault condition, then and then only the incomer circuit breaker should operate first in order to prevent equipments from getting damaged to the incomer side also, or the fault should not be feed from the to feed the upstream also. So the protection should be done in such a way that the feeder at which fault occurs should only operate first. But if still fault exists or in the system, then and then only the incomer feeder should operate. So protections coordination should be done in such a way only. Now, little bit I am going backward, backside in previous slides. Here you can, in this image, you can see the numerical relays has been picturized in this slide. Earlier, were having electromechanical relays, which are operated in a disk, which are having the induction disk, or they are having an induction cup disk, which rotates when any fault occurs or any abnormal condition raised in the system. So these relays provide a tripping contact at the time of the fault, and it will sense this fault and give a tripping and issue a tripping command to this to this switch gears. So nowadays, compared to earlier, the electromechanical relays were sluggish in operation, and many times they are very slow to detect this fault condition. So nowadays, modern technology has been there, and with the help of these modern technologies, these relays are getting modernized with the numerical relay or IED relay, means intelligent electronic device. These relays are having many features like current, voltage, and measure. As I said earlier, that it measures the current, voltage, frequency. It also measures the power which is supplying to that particular network. And likewise, it is also having many features with the connectivity with the automation. It will also augment it with the new technology in the upcoming technologies, like we can see the PLC SCADAs. So for the better advancement, the electromechanical relays are nowadays getting replaced with this electromechanical relays, which are very fast in operation and many protection functions are covered in this only single unit. Earlier, we need to use that separate units for electromechanical relay. If we are going for electromechanical relay, we need to use separate compartments for separate relays. Like as we have studied for overcurrent protection, for protection we need to have two, at least we need minimum two overcurrent and one earth fault relay, right? So this has been eliminated with this numerical relay. Only in single numerical relay we can give protections to all the for all the two overcurrent as well as a single earth for earth fault relay. So this two overcurrent and single earth fault relay has been summarized in this only one unit called IED, or we can say numerical relay. So whenever if we are setting this relays at a particular value, then then if the quantity, or if the current, let's say for example, if we are setting current for this relay as a 10 ampere, and when it then the in normal in faulty condition, this 10 ampere will raise to a certain value. It will cross this it will cross the value, it will be much higher than this 10 ampere. Then value will be crossing this threshold value. At that time, this numerical this relay will be give a pickup value, uh, will issue a tripping command to this circuit breakers, and it will isolate the system. So for going for relay coordination, we need certain values. For doing relay coordination, we need to have certain data required for this, for to coordinate our network. So what are the data required for this relay coordination is a single line diagram of the system. Means if we need to coordinate any network, we need to know we need to know the entire network from downstream to upstream. For this, we need a single line diagram. We need the equipment details, like what are the equipments are connected to the network, like transformers, generators, motors, capacitor banks, if there is any capacitor banks, if there is any reactors installed, if this motor, as I said, then all the details of this connected equipments is required. The impedance of all the equipments is also required in order to calculate the short circuit or fault current, how they are being connected to the network, what are the voltage levels, what are the phase sequence. These all data are required. What are the operating philosophies is there? There is a two line coming, three line coming to the network. If any, there is in-house generators for generating power to for this network. System study fault levels is also required in order to get the fault current ultimately, as it's not possible to practically to see this faulty condition, to get to know the fault current practically. We need to have some system studies which can give us an idea that how much fault current will be there if any fault occurs in the network. So that detail is also required. Then maximum load demand will be the maximum load demand and the connected load, such that accordingly we can set our relays, we can give settings to our relays. The CT and PT ratios, VT ratios, that current transformer and potential transformer ratios, which are used for the protection and measurement device. If there is any future expansion is expected in the network, or any special considerations for any applications required for their network. These data are required to for relay coordination or to perform the relay coordination study. This is a one line diagram, typical one line diagram. Just to get aware, I have covered this one line diagram. the power is getting from the EHV transmission line. There is a generator transformer. The generator is also feeding to this network, and there are two outgoing transformers. You can say UAT A and UAT B. They are further feeding power to another substation or another network, to another load centers. So this is the single line diagram, and then further it gets the transformer is getting stepped down, and it is feeding to another location at a 3.3 kV, and then the another outgoing will be there. Here you can see that at 11 kV there are the generator is feeding, generator is generating the power, and it is feeding to the two transformers UATA and UATB, and the power from the grid and is also feeding to a network that is from EHV bus, and this power from EHV means high voltage, it's get with the help of this GT, it's get stepped down to 11 kV, and then it's further feeding to the another network. So this is a single line diagram. Here the NC indicates the normally closed, NO indicates normally open. So as I said earlier, that we need to understand the operating philosophies. Means the in normal condition, if we are having power from EHV line and from the generator, then there will be a then the fault current of the system will be different. And if only grid is only feeding the power, then the fault current will be different. So for this relay coordination, we need to understand the different operating philosophies of our system. Here also you can see this NO, it indicates that normally open. The power from the D point to this 11 kV ST bus, it's normally the line between this is open, and from here on, and also it's open from this end from UATE bus A. There's a 3 winding transformers connected to our network. Subsequent in the like same way, it will feed to the another location, or it will step down the voltage to the 3.3 kV, and it will feed the power to another outgoing locations. Here now let's come here at this location. Normally there is a scheme that two incomers and a one bus coupler scheme is there. In normal condition, the bus coupler will remain open and incomer feeders will be in a line. So you can see here the NO indicates normally open. So the bus coupler at a 3.3 kV will be normally open, and the two incomer from the transformer B and transformer A will be feeding power to the network. If any of this incomer feeder gets isolated due to some kind of maintenance, or if fault occurs, then this incomer feeder will isolate will be normally open, gets open, and the bus coupler will come in a closed manner, such that the continuity of the power will be there. There is no interruption for the power supply. So normally we can say this scheme is a two incomer one bus coupler scheme, and two incomer feeders will be in a line and bus coupler will be in operation condition. And if any one of the incomers gets isolated, gets open, then the bus coupler will be in a line. So we can say it's a n-1 contingency of this network. So here, to protect the system, we need to see this single line diagram, that how the connection or the network is there exist, how the existing network is connecting and feeding the power to the network. So normally the coordination is done for the overcurrent protection, that the coordination will be done in for the current protection. And for voltage protection, it will, we can say the coordination is based on this overcurrent and time basis. The voltage protection will come in a separate protections, we can say, in a separate protection feature, we can say. But the coordination is done for overcurrent, on the basis of current and time discrimination. So in order to protect, if any kind of fault occurs, here we can say in this single line diagram, one line diagram, that if any fault occurs at 3.3 bus, then this incomer feeder should isolate first, and then only if this gets failed to operate, then the feeder, primary side of this transformer should operate. As there are numerous equipments connected in the network, so for every equipment there are certain special protections being take care for the protections. So to protect this transformer, we can say there are certain protections like differential protections, but source protections for internal fault, to protect the transformer from internal fault, restricted earth fault protection, there's REF protections for this transformer, differential protections, we can say. So for this, for every protections, there are some ANSI code defined as per the IEEE standard. So here you can see the ANSI codes for the protections or the protection device. That is, if there is an ANSI code 2, then it's for time delay, 21 for distance, 25 for synchronization check. Synchronization check means if there is a two source feeding to the particular network, and at that time that two source will be in a parallelly feeding to the network, then there is a synchronization between two source. So for this synchronization, we should have the synchronization check relay, such that it checks the synchronization of both the sources, and accordingly, if there is a mismatch, then it should isolate the source or the faulty source, unhealthy source, in such a way that there is no interruption in the power supply. Another protection code 27, that is under voltage, 30 enunciator, that if any fault occurs, then there will be a rise in the alarm. There is alarm rise in this for this fault, and this alarm rise will be in the enunciator. At the enunciator, we should acknowledge that fault, and accordingly, it will give alarm signal to the person to take necessary actions for this fault condition. The 32, the directional power, we can say that if there is a two source, let's go to the previous slide. If there is a two source feeding to the power, okay, then it should be in such a way that the protection should be given in such a way, in a directional way, such that no power should feed to another source. Means if there is a power from this grid and EHV bus, then it should not feed this generator. Otherwise, there will be a fault condition occurs in generator, and generator will get damaged. So for this, we should provide different directional protection, such that it detects the direction of the power or of current, and it should give a trip command if the direction is not being fulfilled. 37 undercurrent under power, 40 the field failure protection, that is for the generator. 46 reverse phase, we can say negative phase sequence use in our system. Particularly this is used for the motor protection. Negative phase sequence, we can say for this motor protection. 47 phase sequence voltage. If there is a voltage shift between the three phase, then this protection should be in a line. Thermal protection, that is for use for the cables, motors, for such that the motor or cable should not be get thermal overloaded. 50 instantaneous overcurrent protection. This is for the three phase short circuit fault protection. It should instantaneously operate if there is a fault. We can say instantaneous overcurrent means primary protection. 51 AC time overcurrent protection, that is it depends on the time. this we can say inverse time over current protection, IDMT protection, that it depends on the time and as well as the fault current. If fault current increases, then the time current then the time of operation will be lesser, and if fault current is less, then the time of operation will less. I can say less in the sense of over in terms of over current. So as soon as the fault current rises, the time of operation will be minimum. 59, over voltage condition, over voltage for over voltage protection. 60, voltage voltage imbalance protection. 63, pressure for transformer, we can say this is used for the pressure gauge. 64, apparatus ground or we can say apparatus, in this it means the equipment ground protection. 64 means earth fault protection. REF protections generally used for these transformers or motors. So 64 protections will be take care this ground fault protections for REF protection for transformers, generators or motors. 67, AC directional overcurrent. As earlier I said, for directional power it's 32. 67 is for overcurrent protection. Directional overcurrent protection, it will detect the direction of the power, and accordingly if there is a reverse flow of the power of the current, then it will detect. 68 means blocking, that if for particular time of interval, if we need to block certain protections in order to meet the production demand, or some other reasons of maintenance, we can block this particular protections in numerical relays. Nowadays they are having such features. Likewise, another there are certain codes for the protections. It's been listed in ANSI 37.2 standard. The 87 for the differential protection, 81 for the frequency protection, 94 to give the tripping command of the circuit breakers. We can say TCS, trip circuit supervisory command. There is 94, 95 we can select. So these are the certain protection ANSI codes for power system protection. Okay, let's go in a deep for relay coordination. So relay coordination can be done based on the two criteria or two discriminations. We can say first one, time discrimination and current discrimination. Combination of both is now is generally used for reliability purpose, that is by both time and current discrimination. For better understanding, let's see on the figure on the right hand side. So here you can see the single line diagram, a typical single line diagram, transformers feeding power to this network. This is the incomer feeder for this bus. Then further it's down the downstream, it is feeding to another location, and then it is feeding to the consumer end or at another network, another load center. So you can see the for time discrimination, we should give time grading to the operation of the particular network, particular relays. Here you can see the CTs. So CT, this the symbol is termed as a CT. This is symbol is of circuit breakers. This is the symbol of relays or the protection relays used for the protection scheme. 50, 51 and 50 means AC over current, time over current protection. 51 and that is AC time over current for earth fault protections. 50 instantaneous protection. So 50 will be the primary protection and 51 will be the backup protection, we can say. So likewise for these feeders also and for the downstream feeder also. So the in time discrimination, we should discriminate or we should give a time margin in such a way such that if any fault occurs at this feeder, we can say for this network, for this, then you can see that for this network, the fault should be isolated, fault should be cleared in instantaneous in a definite time. That is, we can say it's in 0 milliseconds. Fault should be isolated in a 0 milliseconds. If this relay fails to operate or fails to detect this fault, then there should be a certain backup protection. We can say 51. So it should operate in a 300 milliseconds for the time grading. The time grading given should be given in such a way, such that the another outgoing feeders connected to this bus should not isolate. So the time grading should be given in such a way, such that for these fault conditions, these feeders should not isolate first, and the feeder which is feeding to the downstream network should provide a backup protection. Likewise, similarly, if these feeders also get of this relay should also get fails to detect this abnormal condition or a fault, then the upcoming feeder should be provided backup protection to this downstream network, and it should operate in certain time in grading margin of 300 milliseconds or 200 milliseconds that we can set. And this feeder should give a better backup protection for this downstream network. So the discrimination or the grading given is based on the time. The red indicates in the timely based manner. The red or orange line indicates the timely based time discrimination, relay coordination done on the time discrimination manner. Now for current discrimination, we can say the feeder should operate that for minimum fault condition. If the fault condition will, as we go from up to downstream, the fault current will be, we can say fault current will be lesser compared to this upstream, because of the impedance coming in the picture of the certain equipments or the cables connected to this connected to the network at which fault occurs. So we can say the fault current at this particular network will be lesser, and for upstream or the for upstream network it will be much higher. So the discrimination should be based in terms of the current, that this breaker should be such in a such a way that it should isolate with a minimum time, with a minimum current. If certain current gets beyond the certain value which is set for this breaker, then only this breaker should operate. And if this breaker or this relay also fails to operate, then and only then this should be operate, and the current will be higher at this particular location. Now the third one is by both time and current discrimination. We can say this is the best and ideal manner to provide relay coordination in such a way so that it should completely coordinate from downstream to upstream network, and it's a reliability given in such a way that if fault current exceeds, as we can't predict the how much amount of fault current will be there if certain fault persists in our feeder or in our network. So with this, we can provide protections based on the time and current discrimination. And this time and current discrimination will be done on the basis of the time current characteristics curve. We can say that is the time current characteristics curve. This characteristics curve will be has been shown over here. You can see in this graph or the curves. You can see there are certain curves. There is definite time, simple inverse, standard inverse, normal inverse, both are same, very inverse, extremely inverse, and another is long time inverse protection. To coordinate the LT network that which is equipped with a fuse, or we can say low voltage circuit breakers, we generally use extremely inverse curve and for very inverse curve to coordinate as they are with the fuse or MCBs connected in the downstream network, as they are having such characteristics to match which can match easily with a fuse and the circuit and the MCBs of low voltage. So we use very inverse and extremely inverse curves. And likewise for relay to relay, we use simple inverse curves and long time inverse curves for to coordinate the network. You will get a better idea when we will jump to the ETAP section, when we will having some examples, practical examples on a ETAP. Then we will having the better idea. You can visualize the same thing. So as I said, that protection relay coordination is done on the normally for the is done on the normally from time and current discrimination, and the coordination is done for the current based protection. We can say that coordination is for the current based protection. So normally there are two types of protections: phase fault and earth fault protections. Earth fault protection, and we can give in a the protections should be given in a certain manner, that is for load overload protection, inverse definite time protection, and instantaneous phase and earth fault protection, we can say. Nowadays, numerical relays are having all these features in a single compartment rather than using the 3 unit or different units for every separate protections. So the ID based protection, that we can say multiprocessor based numerical over current relay, which is having the following protections as a minimum, as a basic protection elements. That is phase overload protection, inverse definite minimum time protection, and instantaneous phase over earth fault protection. Then what is phase overload protection? Phase overload protection is which protects the equipment from electrical overload, which if it should not exceed the continuous rating of the equipment, of the product equipment. That we can say the motor, generally for the motor and generators are having such kind of overload protections. If we are motor is having a rated of 75 kilowatt, then it should be having certain characteristics, that it should take overload of certain 80 kilowatt, up to 80 kilowatt it can withstand. But if it goes beyond 80 kilowatt, then the motor should gets damaged. So in order to protect this equipment, we are having this phase overload protection. Another protection is termed as IDMT, overcurrent protection. The selectivity of overcurrent protection relay can be achieved by applying this, as I said, the time or current grading in inverse definite minimum time protection functions. Another protection is for instantaneous overcurrent protection, which protects the feeder and transformer against the short circuit, including the bushing terminal faults of the transformers or its switchyard. The ANSI code used for this instantaneous overcurrent protection is 50. For IDMT, that is time overcurrent time inverse defined time protection, it's a 51. And thermal overload, that is phase overload protection, the ANSI code is 49. For this, in order to protect these equipments, we need to give certain settings to the relay, such that beyond this, if the parameters goes beyond this value, then it should operate. The relay should operate and raise a command to isolate, to detect the fault, and it will isolate the faulty section. So this is the relay setting calculation. That how the relay setting calculations can be done. And there's certain, before going to the calculation, there's a certain terminologies which is used for relay settings. That is the pickup value. It is the minimum value for actuating quantity at which relay starts to operate. Means it's a minimum minimum quantity or the minimum minimum value at which relay should trigger the tripping command. Relay should trigger and gives tripping command to the circuit breaker. Plug setting multiplier, which is the based on the pickup value and the rated city current, that based on this we need to give certain settings to the relay, which will be getting inputs from the cities. So the plug setting value, pickup current divided by the rated secondary current of the city in terms of percentage. Plug setting multiplier, it is a ratio of the fault current in the relay coil with the pickup current. The time multiplier setting, time multiplier setting, this is a term as a TMS, means desired time of the ratio of the desired time operating time of relay at relay operating time selected for the selected PSM, and TMS at 1. Relay operating time means at what time relay will operate. If we are giving the certain time intervals, then for certain value of the fault current, at what time relay will operate, how much time relay will take to operate for the particular fault current. So for this there is an equation, we can say the TMS into K, which is the constant related to the curves. I by IP means measured current divided by the pickup current minus 1. So with this value we can set the certain parameters in the relay, and accordingly relay will measure the quantities, the current values, and if it goes beyond the threshold value, then the relay will start to trigger. This relay will trigger and operate at a certain time of a certain time period. So this time period can be known with the time current characteristics curve. So there is a TCC, we can say time current characteristics curve. For certain curves there are at TMS there are, you can see here, आप यहाँ पे देख सकते हो इस राइट हैंड साइड फिगर पे कि for this particular how much time relay will take when it is at TMS1 for every curves. हर एक कर्व के लिए यहाँ पे प्लॉट किया गया है कि ये कितने टाइम में ये ऑपरेट होगा if TMS is 1 and for particular current value. So with this we can determine the time of operation with the help of this parameters for K and infinity is given for different types of curve. That is for short time inverse curve, the K parameter is 0.05 and infinity is was 0.01. The question mark is infinity here. The standard inverse, that is 0.14 and 0.02, that infinity. This value should be placed in this equation. This value should be placed in this equation, that is K. You can see K. Let's take example for standard inverse. The K is 0.14 and infinity is 0.02. Such that it should be put in this equation K, that is 0.14, and infinity it will be 0.02. And the value measured current value and the pickup value at which we want relay to operate. So with this parameter we can have relay operation time. Earlier, to discriminate that for time intervals, the discrimination was defined as a 0.4 seconds, that is 400 milliseconds, to be applied for downstream to upstream relay in order to ensure the selectivity due to the overrun of induction disk. Means in earlier time there the protections were been taken care by the electromechanical relays which are having induction disk. So this was sluggish in operation and it takes more time to operate this relay, such that the discrimination or the time grading was given for of 0.4 seconds. Nowadays, in numerical relays, there is no disk, therefore there is no overrun will be there, and hence we can reduce the time of operation in order to isolate the faulty section as soon as possible, and another healthy portion should not get affected. Therefore, time discrimination has been reduced to 0.2 seconds, that is 200 milliseconds, can be applied between two curves. The time discrimination applied between two curves should be 0.2 seconds. You can see here in this time current characteristics curve that for 33 kV bus, for relay 1, which is the downstream, it should operate first, and if fails to operate, then relay 1 will operate after the certain time margin of 200 milliseconds. See here in this curve, you can see the relay 2 curve, relay 2, that is relay 2 is operating at 0.1 seconds, and for instantaneous protection, and for the same, for backup protection, if this relay 2 fails to operate, then relay 1 will be in a backup, and it will operate at a time margin of 0.2 seconds, that is 0.1 for downstream, and for relay 1 it will time interval has been set accordingly with the margin of 200 milliseconds, such that this relay will operate in 300 milliseconds. So the time margin you can see in this plot, आप इस plot पे देख सकते हो कि time margin जो दिया गया है वो है 0.2 seconds, 0.2 seconds between these two curves. Between these two curves is the time margin is been set to 0.2 curves. This guidelines is also given in IEEE standards 242 used for the relay coordination, IEEE 242, that is buff protection for industrial plant coordination, is also defined in this standard also. Up to here, if there is a certain questions we can take to solve the queries of our participants, and after that we can switch to the ETAP examples.
Kashish, what we'll do is we'll go to the ETAP analysis and then we'll discuss the queries. Maybe people are waiting for you to solve the case study in ETAP.
Okay. Okay. So let's move to the ETAP. Okay. Yeah, our screen is visible, ma'am.
Yes, yes, Kashish.
ETAP screen is visible, no?
Yeah, yeah.
Yeah. Okay. Okay. Sure. So now let's have a practical example of this ETAP. As I said in this session, that we need certain data to perform this relay coordination study. To perform this relay coordination study, we need certain data, that is single line diagram, in order to model this network in this ETAP. So likewise, I have one typical single line diagram which has been modeled in this ETAP. So just before going ahead, let me familiarize you people with the ETAP. ETAP is a simulation study software which is having vast library of numerical relay, which is having a library of relays, circuit breakers of different manufacturer makes like Siemens, ABB, Schneider's, etc., GE, Alstom. So this ETAP is having a vast library of existing numerical as well as electromechanical relays, so that we can check the parameters, we can check the coordination of the entire network. Also, ETAP is used helpful to evaluate the short circuit as well as the load flow studies of our network. So with this ETAP, there are certain elements has been listed here, which is having the component library. We can say, yes, you can see here, there is a component library which is having certain components like bus, transformers, three winding transformers, cables, transmission line, reactors, certain branches, grid. There is a power from the grid, generators, PV array, motors. PV means a photovoltaic module, the wind turbine generators, motors. Likewise, there are many components which is helpful to evaluate the certain studies in this ETAP. So with this, at least what we need is we need the certain component equipment details which has been used in our network, which is used in our electrical system, as well as for measurement purpose, the CT, PT details, circuit breaker details for the protection, in terms of protection. These all details we require to perform these studies. So before going to this network, let me go to another section, another side, such that you guys gets familiar with how to model the certain network in ETAP also. So let's model start with the basic thing. There's a grid, power from the grid. So here we will model a grid, take a component from this equipment section, grid. Then from this grid, power from is fed through a overhead transmission line. So we will take a transmission line here and we will connect this transmission line with the grid. So with this, here we can define the voltage level in, let's take for the grid. In grid, we need to define the voltage level. For at what voltage level we are modeling the system. So for rated kV, we can say we are modeling for 11 kV system right now. Now short circuit parameter, we need to have the details of fault current, system study fault current details. If we are not having, then we can ask the utility. Utility, that means our generation company or transmission company or distribution company, they are having these parameters. For here we for example, as I am taking 31.5 kilo ampere set as a fault current for 11 kV network. So I am modeling this 11 kV grid with a fault current of 31.5, maximum 31.5 kilo ampere. Then I will model the transmission line. Here in this parameter section, conductors, different type of conductors has been listed in this ETAP. You can see we will go with there are different type of conductors, that is zebra conductor, wolf conductors, panther conductors, dog conductors, lemon conductors, orange conductors are also there. So here let's go with lemon conductor. Here in this library, let's select the lemon conductor. Here with this, all the parameters of the lemon conductor will be fetched from this library. We don't need to input any kind of parameters. ETAP will having all the details of these conductors. Okay, then after we need to we will require PT, that is potential transformers, for protection as well as for measurement purpose. So we will define the PT voltage ratio of the PT will be set here, 11 kV of primary side and 110 volt for secondary side. Then there will be a CT current transformers for protection as well as for measurement purpose. Let's take this CT ratio for our network, that is 60 bar 1. I am having certain parameters, that's why I am just taking simple this kind of data. This data you will get from the of the network single line diagram. You will get all these details from the single line diagrams. All we need to ask the user or the industries or the plants to provide these certain details. Then we are having this circuit break current transformers. Then we will take a relay. Here we will take the relay from this component list, the relay, joining this relay, connecting this relay with the circuit break current transformers. The relay has been taken of the Siemens. We can also change certain relays with a certain makes. As I was said earlier, that the ETAP is having vast library of different manufacturers, that is ABB, Allen Bradley, Alstom, Areva, Besla Electric, then Eaton, GE, Mullin, GEC, General Electric Company, Hitachi, L&T make, Mullin Jain, that is nowadays is Schneider make, PNB nowadays is taken by L&T, Railroll, Schneider Electric, then Siemens. So let's go with the Siemens make. Siemens make 7SJ62 relay I am taking. So Siemens make 7SJ62. Here you can see the relay name and the relay model name and OEM make name. Now here the certain parameters we need to we need to set in ETAP after certain calculations. After calculating the relay settings, we need to input these parameters for the relay for relay coordination. The settings we need to give to this section. Then we will have we will have a cable, sorry, circuit breaker. We will have circuit breaker, ST circuit breaker. We will have let me okay, the circuit breaker of different make. We can say a General Electric make, IBB, Alstom, Siemens. Let's go with a General Electric make. Here you can say as the system is 11 kV, the maximum voltage will go with up to 15 volt as per the library which we have selected. The continuous ampere rating of circuit breaker will be 1200 ampere. The breaking capacity of the circuit breaker will be 37, or we can set as per our details. We can also set by another parameters which actually exist in our circuit breakers. So let's take with 50 kiloampere of circuit breaker. Maximum make capacity, as I have increased, then this will also gets changed with a margin of 2.5. We can say symmetrical current. The time constant of the circuit breaker, it will automatically fetch from this library. This much detail we need to give. Then we will have a bus of our premises. (11 kV bus, automatically modeled. Then transformer, simply like this we have to model the entire single line diagram, not taking much more time. Let's go to the system which I have already prepared for easy understanding. So here you can see a grid and a grid and a generator. Both are feeding at 11 kV network, but the generator is for emergency purpose. If grid power fails, then generator will be in line to continue the power supply. So certainly I have modeled every equipments in the single line diagram. The cables I have modeled for the cables is of aluminum makes single run 3 core 300 square mm the size of the cable. The transformers of 2.5 MVA. Here we need to input the parameters of the transformers, that is 2.5 MVA transformers. Here it will automatically fetch all the details. We only need to give uh, rating of voltage as well as the MVA rating of transformers, its impedance level of the transformers. If we are in a designing purpose, that is from the greenfield plant, then we don't have any exact parameter values, then we can assume the typical parameters. But in order to have accurate result, we need we need an accurate data, so that this all the details will be available from the nameplate, and that parameters have to place over here. Then the tap position, whether the transformer is on load tap changer or off load tap changer, is also we can mm, give input in this section. Then the grounding section, how the transformer is grounded, what are the winding configurations of the transformers, whether it is a delta star or star star transformer. So here we have transformer of delta star one, delta star. Delta is on primary side, star on secondary side, and star is also grounded with the solidly grounding. Is grounded with the solidly grounded system. And the vector group. What will be the vector group? So it's a as we have certain vector groups. So dy11, we can say here dy and 11. So the 11 is for phase angle between the two windings is a minus 30, means 11 in a clockwise we can say, then it's a 11. It's HV leads LV by 30° we can say. Likewise, these all parameters of the transformers should be implemented. Then the feeder bus duct will be there, which will feed to the MCC or LT section. This is the LV circuit breakers, low voltage circuit breaker, which is having inbuilt trip unit, means release feature, as we which will work for protection. It will protect the system from the certain faults. So this is the trip device we can select from this library. For square D, I have taken NW40 model for micrologic trip unit. Its rating is 4000 ampere. The trip device, that is LSIG, means long band, short band, and instantaneous protections we need to give. Then the ground fault protection. For ground fault protection, there are certain setting parameters which we need to implement here, which we need to give as an input in this section. Then certainly the outgoing loads, that is lump load, the motor feeder connected to this network, any lightning load connected to this network with a different rating, so of different parameters. So likewise, a typical network has been modeled over here for easy understanding of this relay of this system. Now let's go for relay settings calculation side. In order to calculate relay settings, we need to have certain parameters like what kind of load connected to our system and what is its full load ampere. Now let's say here for lump load, the full load ampere is 788 ampere. So we will set overcurrent protection in such a way that it should if that current goes beyond its rated ampere, that is 788 ampere, then this trip unit should issue a tripping command for this particular section. So for long band which is used for the overcurrent protection, we have given a margin of 5% of this 788 ampere. We have given a margin of 5%. for normally overload. We can give margin up to 25% for overload depending upon our requirement and depending on the production need. We can give up to 25% overload margin, but here overcurrent margin. But here I have given the margin up to 5%. I can say, considering the parameters of the trip unit. So here the 5% of 788 ampere is 795 amps. 795 amps. But in order to not having exact value in the relay, we can say we have considered it as a near to 800 ampere. So here you can see we have selected to 800 ampere. Then the short circuit time. The short circuit time depends on the short circuit current. Normally the fault current will be goes up to 10 to 12 times of the full load ampere. In order to protect the equipment, we set these parameters to the four times of the full load current, that is 4 into full load ampere. 4 times we can set, and as there is no downstream, यहाँ पे और कोई downstream network नहीं है, so we will adopt the time delay, minimum time delay we will adopt, that is 100 milliseconds. This is the instantaneous protection, that is within 0 milliseconds. If any fault current goes beyond certain value, then it should operate within 0 milliseconds. So we will take this protection in line. Likewise, every parameters has been set for every feeders. For motor feeders, also we have given settings to the motor feeder. You can see over here. Now let's set this motor feeder. The motor is of rating 250 kilowatt. Now the full load ampere of this motor is, you can say, 406 ampere. So what will be its full load overload current with a margin of 5%? So it will be around 427%. 427 ampere. If we are considering the overcurrent margin of 5%, then it will be the threshold value which we are setting is 427 ampere. So here we need to set this trip relay in such a way such that there is a if current goes beyond 427 ampere, then it will start in operation. It will come in operation. So with this parameter, we can set up to 4.55. The range which we are having is 424 or 432. So little bit higher we will go for the safety margin, and we will set to the 432 ampere. Now let's go for 4 times. If current goes 4 times of the load ampere, then we need to isolate this motor to get to protect from the damage. And instantaneous we will go to the 10 times, as normally the fault current goes for 10 to 12 times. So we will go here for 10 times and normally for 0.1 seconds. Now for ground fault protection, normally the ground fault protection is setting is done for 20% of the full load, 20% of full load. But here for this micrologic relay, the parameter ranges are from A to J. Parameter are range from A to J, and if we for every parameters there is a certain current range. You can see if I'm changing the setting value, you can see here the range is also gets changed. So we will add up 0.2 into 20% of 400, and we will the full load current, that is 406 ampere. So we will set here the parameter as 0.2 into 406.8, that is 81 ampere. but the minimum available range is 160 ampere. So we will go with 160 ampere here with a time delay of 0.1 seconds. Now, in order to give settings of this lightning load, same procedure we will follow. That is, full load is 141. Now, with a 0.5 percentage margin, 0.5% of margin, we will set this circuit breaker at 150 ampere, nearly 150 ampere. We can say, okay. Now the minimum range for this relay here, we also need to check the minimum range of the particular relay which we are using for protection, or the particular trip unit which we are using for the protection. We also need to check this minimum available range. If we are not having this minimum range, then we should go for minimum available range, or we need to replace this trip unit. So here minimum available range is 160 ampere. So we will go for 160 ampere. Likewise, short circuit for four times, and fault current instantaneous protection for 10 times. Time delay 0.1 seconds. Accordingly, we will set here. Now for this incomer feeder, same way setting will be done. Now for this incomer feeder, the setting will be done in terms of this transformer secondary side. That is 3033 ampere, 3333 ampere. The reason behind going for this transformer secondary side, that if we are expanding or this network in terms, if we are connecting some another network in future, then we don't need to change this parameter, and this parameter should be able to withstand this expansion also. So we are setting this trip unit to the 3600 amperes, that is 10% margin of 3333 ampere. The reason behind going for 10% margin, such that it should withstand if certain overloads exist in all these three premises. For that, we have given a 10% margin, short circuit for 4, and instantaneous for 10 times. Now we will go for this relay. The relay is set in such a way such that it should match this curve should be matched with this circuit breaker of LV section, and it should able to withstand any fault current if exists in a downstream network. That is the primary ampere which we have taken into consideration is 131, and 10% of that, the relay has been set with the 144 ampere with a time grading margin of 300 milliseconds for this particular fault current, if for as a backup protection for this particular fault. How I have calculated this, I will show you here. Let's first of all for this we need to calculate the fault current. With this ETAP we will calculate the fault current. What will be the fault current? Okay. So if any fault occurs in the system at this bus 121, then the fault current will be 13.72 kiloampere. And if any fault exists at this network, then the fault current will be maximum fault current. This is the maximum fault current condition. That is the 53.38 kiloampere. Now, if we go for minimum fault current condition, then we can adjust from here in ETAP what will be the minimum fault current condition. Let's say the minimum fault current will be 46 kiloampere. So relay coordination is done based on minimum and maximum fault current condition, and accordingly we need to calculate the settings of this for this particular fault current. I will go for maximum fault current condition, such that for maximum automatically it will calculate for minimum also. Now let's go with here. Here we are having 53.38 kiloampere fault current, and time delay which we have set here as a 0.1 seconds, maybe 100 milliseconds. Now the time grading margin of 0.2. Here this section will be set at a 0.1. This section will be set to the time grading margin additional of 0.2. That is, it will be set to the 0.3. It will set to the 0.3 set, and this parameter will go. This will, here we will go with the 0.5 for IDMT for IDMT in inverse definite minimum time of operation. We will go for backup protection at 0.5 seconds. So having this detail, we can calculate the parameters for this. For this, we need to calculate the through fault stability or inverse fault current condition of this transformer. Inverse current condition means during the starting of the transformer, the relay should not give a tripping command or should not de-energize the transformer during the starting condition. So for that, we need to ensure that the inverse current condition, as well as that during the starting during the starting of transformer, the relay should not detect this inverse condition as a fault condition. Now let's calculate this with, okay, let me go with this parameter of, okay, with this formula of calculation. Okay, the screen is visible to all?
Yes, yes.
Yeah. So here we are taking the time grading margin of 10% for HT section, and CT ratio, that is CT ratio is here is we can say 150/1. So CT ratio is 150/1. Now we will calculate, okay, 1.1 into 130, 1.8. So it's a 0.96. So the settings which we will give is a 0.96 to this HT bus to this relay, that is 0.96. Now fault current, that is the PSM. We need to calculate the PSM, that is the fault current of this particular section. Now this fault current, as we have seen, that is 53.38 kiloampere. So for this, the fault current, there is a transformation with this transformation ratio, means what will be the reflection of this fault current at this section, that we need to calculate. So for this, we will do the reflected fault current. This we need to calculate in order to withstand during the through fault condition. That is, if fault occurs at LV side, then our ST section should not get tripped first. Only the LT section should get tripped for the genuine fault. So we need to calculate. So the fault current calculation, you can say the fault current is 53.38 kiloampere divided by its transformation ratio, that is 11.0.433. Okay. Can you calculate, ma'am? What? Okay. So it's 2.101 kiloampere. Now with the help of this 2.101 kiloampere, we can determine the value of TMS for this relay. So we can determine the value of PSM. So the PSM, we will consider the IF means a fault current, that is a reflected fault current, that is 2. I will say, I will write in terms of ampere, 2101 into, okay, no city ratio, this city should be the one, that is PSM is here 0.96. Okay, so it's around 14.59. Now as with this help of this PSM value, now we need to set the TMS value here, or TMS value, but for this, for the coordination of this section with the LVCB means trip unit, we need to check this curve, that which curve will be having the similar properties or with the matching properties with the fuse. So this can be checked with the star plot of this ETAP. You can say I'm creating the star plot for this particular network. See, okay, certain curves are here. Let me show you all the curves. Okay, wait a minute for easy understanding. Let me run first of all for circuit condition. Yes, no bus was faulted, so let me just fault this bus, get fault. This bus also get fault. Now let's run short circuit condition. 58, 80 minutes. Okay. For maximum condition, we need this. .38 kiloampere. Now going for the star plot, we can see this. This is the curve of this LV circuit breaker, and this is the curve for this HT transformer primary side relay. The curve should be such that it should match the tripping command of this LV circuit breaker. Now, if we are choosing this normal operation curve, then what will happen? Then it will go beyond it will overlap this. Sorry, it will overlap this relay. You can see this. You can see here it is overlapping the curve here. It is overlapping the curve here with this LV section. So this is not properly been coordinated. In order to coordinate this net LVCB with upstream, we need to change the curve. So we will, what we will do, we will only just change the curve for extremely inverse section, and we will adjust the TMS. We will adjust the TMS value. Okay, and the through fault condition also we need to check. The through fault which I am talking means, you can see this is the fault current value for this circuit breaker. If any fault occurs in LV section, then this relay should not operate first. Now what time, what condition is is happening, that for any fault condition, we can see for any fault condition this relay is getting tripped first, right? See, for any fault in HV section, the incomer relay is tripping first, then the circuit breaker 2 is getting tripped second, and this the fault if a genuine fault occurs, the circuit breaker is getting tripped last. So this is not properly being coordinated. The system is not being properly coordinated. In order to coordinate properly, we need to set parameters in such a way such that these feeders should not operate first for any fault condition at downstream network. So we will set this setting in such a way, we will go with extremely inverse, and for extreme inverse parameter, for I and K, we can see the K factor is 80 and infinity factor is 2. Okay, so what we will do, we will change the parameter over here. We will go for 80 and we will change. Okay, this is the PSM value, that is 14.9 divided by what is the 2. Okay, so we will have a certain value, that is 14.4 raised to 2. So we will have the value as 0.382 seconds when TMS is set at 1. Now to set TMS for desired time of operation, that is for 500 milliseconds, we will do 0.382 seconds, then 0.5, it will be around 1.3. So with this we can calculate TMS as a 1.3 and we will give input here with this parameter, that is 1.3. Okay, now you can see here that this is getting somewhat overload with this feeder. So also we need to check this curve and we need to change this TMS value simply by grading instead of 500 milliseconds, we need to increase the time delay to 600 milliseconds. That also we need to get ensure. So 0.6 divided by 382, that is 1.57. Okay, 1.57. Okay, accordingly this is set. And now for this through fault condition also, this setting should be such that it should not cross the damage curve of the transformer and it should withstand the inverse condition. So with this we can set that condition, that is I double greater, means instantaneous protection, or we can say short circuit protection. That is 1.3 into 2101 . This 210 is one is a reflected fault current. At 11 kV divided by CT ratio. That is 27 this term IN, it means CT secondary. CT secondary is here 1, that's why I have written I into IN. Now this is set to here in this instantaneous protection, that is 18.2, and the time delay is a minimum 0.1 operation. Now here you can see the curve has been slightly shifted to this condition, but still it's crossing this condition of LT fault, not cross. Okay, so again we need to change this parameter. We can go for 1.5, 1.3 or 1.5 times of fault current. 1 point. That is, we can say here set. Now see, for through fault condition, it is getting protected, that for through fault, for any LV fault, this will not operate first. That is, as we have said it for 0.15 seconds. The reason, okay, sorry, let's take for 0.1 seconds only, such that for as the voltage level gets changed, so we can start here these settings from minimum value, that is 100 milliseconds time getting with a minimum time delay of 100 milliseconds. Accordingly, the certain relay settings has been adopted and gets changed. So the same setting will be changed here, 1.5, the 21 and 0.1 extremely inverse. We have taken 1.57. Okay. So similarly 1.57. As the rating of all the transformers are same, so I am taking all the transformers 2.5 2.5, so I am taking all the same similar settings, and accordingly I am changing the parameters over here also for this. Okay, now with this we need to check, we need to set this feeder also such that the summation of these three transformers will be as the full load ampere of one transformer is 131 ampere. Full load ampere is of 131 ampere, 131 ampere. So for three load, it will be around, for three transformers cumulative or summation, we can say it's around 393 ampere. So for this, we can say here sum of these three, the sum of all three transformer is 393.6 ampere. So incomer feeder should be set such that it withstand all three trafo means transformers. So here what we'll do, here set, okay, here we will set this protection in such a way that the another margin for the 10 times of margin, that sometimes if any of the transformer, two transformers are running at a running load, then it should withstand for some overcurrent to some overcurrent condition for certain time intervals. So we will set 393.6 into for 10 time margins, that is 332.96, that is, we can say, six into 1. Now we need primary ampere, that is 432.96. So we will set it here accordingly. Here we will set accordingly, that is 0.68. Now for 0.687, we can see that the value is 432.8 primary amps. It's been achieved here. And for this, for high set condition, we need to set highest among all the three outgoings, that is 3150 ampere. So this should be set. So instantaneous should be feeders, that is, as we have added the same settings for all the three feeders, so I will consider same setting equals to 3780, okay, ampere. So now I will set here, it is 3180. See, 3180. Meter, okay, parameters gets changed. 3780 for 0.3 seconds. The 0.3 means additionally we have taken a margin of 200 milliseconds for this relay, and backup for this relay 0.200 milliseconds, 0.2 seconds of margin has been adapted. That's why it is set at a 0.3 second. Now you can see for any fault condition here in the downstream, the sequence of operation, that is will be in a wait a minute, why it's getting tripped. Okay, we haven't set this TMS value, no, that's why. In ETAP we have a feature, that we can see which protection operate first. So here we can see the relay one is getting tripped in jam protection, but jam protection we don't need for incomer feeder. So we will disable this jam feeder here. We will don't want this protections. Okay, that we will disable that protections. We need to coordinate for the current on the basis of current. So we will give this setting such a way. Now let's see the coordination. See the sequence of operation. If this fails to operate, then this will operate. If this fails to operate, then this relay will operate. Similarly, if fault occurs in this downstream network, then you can also see that the particular section will operate first. If this fails to operate, then this will operate, and if this fails to operate, then the primary side of transformer will operate. Here we can see the time of operation, at what time these relays are getting operate, at what particular value the relays are getting in trip. So as we have said, instantaneous protection, so considering the circuit breaker time of operation, the time of operation is 60 milliseconds. Then we have taken time delay of 200, minimum time delay of 200 milliseconds. So this breaker, you can see the breaker highlighted in red gets operated in 320 seconds. The relay 5 means the primary relay gets operated, as we have said, this relay for 600 milliseconds. So nearly this relay operates at 593 milliseconds, and considering the time of operation of circuit breaker, this relay operated taking at 693 milliseconds. And likewise in 1.3 seconds, 1.3 seconds, this relay, that is incomer relay, operates first. So accordingly we can set certain another parameters here also, we can check this. Likewise in similar subsequent feeders also. So the desired relay sequence has been achieved, relay sequence of operation has been achieved over here also. Oh, okay, let me check this. Let's disconnect. See, likewise this operation goes on. Similarly here we can go with the ground fault protections, and for line to line fault protection also, for to coordinate, to check the coordination. We can see simply by switching off this sequence of operation. Let's go for line to ground fault protection. We can see for line to ground fault protection, if any fault occurs in this section, which relay will operate first. So this is the sequence of operation. Likewise to both the relays, if ground fault protection fails to operate here, then the phase operation will be in a manner, we can see. Okay, see in 80 milliseconds the ground fault operate first, and if it fails, then the phase overcurrent will occur and it will operate at 320 milliseconds, and then it will occur, and then this relay will be operate if the circuit breaker fails to operate for this line to ground fault protection. So similarly, we can set for another other relays also, and the same philosophy has been adopted for this relay setting calculation. While calculation, one must need to see these curves such that it should not get overlapped. This relay should not be get overlapped. Here you can see the all the network. Okay, let me delete this one. Right. Okay. Now see, this is the relay is getting overlap. Here you can see the relay is getting overlap. Now for this I need to increase the time delay. To change this time delay, we need, first of all, we need to have the fault current value, that is of the particular network, that we can check here. That is 13.72 kiloampere. So we will go for 13.72 kiloampere, we can say 0.678, 687, sorry. CT ratio is 630 ampere. That is 31.69. Now here PSM, we can say here the PSM is getting much higher, that is 31.69. So as per some standards, it is said that if the PSM goes beyond 20, the standards we can refer as NPAG and IEEE standard, that is 242. If PSM goes beyond 20, then we need to adopt the time of operation, that is time of operation as 297 milliseconds at TMS1. So here we can set the TMS, we need to time of operation is for 600 and another grading of 200 milliseconds, that is 800 milliseconds. and time of operation will be 297. That is 0.2 TMS, we can say. Now we can check here in this curve. Now we can see that this curve and this curve is properly been coordinated with the network. That this curve and this curve, all the three curves are well coordinated with the entire network, that they are not being overlapped at any point. Here this portion is for the voltage transformation. If here by the help of this long crosshair we can see the voltage transformation current, see 1.6 1.63 ampere which has been set, 1.44, that is the set point which we have set for the relay. And here we can see this current is displayed in terms of the 11 kV, is shown in terms of the 11 kV. So if we change the transformation ratio to 0.433, then we will get 3600 ampere over here. So this is the how the relay coordination is been done with the help of ETAP. With the help of ETAP, here we can also have the setting parameters, that what settings we have adopted, that can also be cross-checked with this plot also. This is the damage curve of the particular feeder of the particular cable as well as the line, which are taken to the consideration for this portion. This is the fault current indication, that how much value or how much amount of the fault current will persist in the network whenever any fault occurs in the system. That you can see for both the relays. See, this is for the LV section bus, LV section circuit breaker. This is for this relay, upcoming incomer relay. This is for the incomer relay. Okay, wait. So this is for incomer base relay. Okay. And this is the fault current for this relay. Relay number 5, that is transformer primary E side. So this is the relay coordination. What actually the thing is, and how we can cross check with the time current characteristics curve. That is all from here with the ETAP. And any questions from our audiences, we can hear.
Thanks, Kashish. Yeah, the room is open for discussion, guys, and you can ask your queries. Either you can put it in the chat box or you can unmute and speak also. Nobody has a question, guys?
You can mail us the
Of course,
question.
and maybe most of the team actually asked for your PPT. Maybe we'll share you the document along with the mail, or you can also post us, and we have given our numbers in chat box, guys. Or you can give the feedback and post your question in that also. Where we get ETAP app or software? The question is from Pranay.
Sorry, can you ma'am
Where
just
we
tell the
get
question?
yeah, where we get ETAP software? The question is from Pranay.
Yeah, okay. ETAP software, you can download a demo version from ETAP website. From ETAP website, you can download this ETAP software. You will get a demo version of ETAP. You need to buy the licensed version if you want to explore more modules of ETAP. So, but for students, there is a provision given by the ETAP that you can download a demo version and you can have some hands-on practice in that.
Okay, there's a question from Sandeep. Same process is followed for 87 protection, that is differential protection.
For differential protection, there is a certain guidelines given in transformer protection standard by IEEE as well as by some another well-known standards like network and protection automation, that the differential protection should be such that in such a way that for all operating in all operating taps it should withstand uh, during the normal running condition. And normally the differential protection is given in a percentage of 20%. That is, if 20% different occur in internal fault, then the differential protection will be operate. So there is certain another philosophy. It will not cover up in this in the coordination portion. It's a kind of unit protection which have certain another formulas for this. So same formula we can't add up for that.
Okay. There's a question from Anand. Can you share some examples of earth fault coordination?
Yeah, sure. For earthfall coordination, we can show the example to them. Okay. Okay. The CTAP scheme is visible now, right?
Yes, yes.
Yeah. Now see, for earth fault, as I have shown that in ETAP we can change the sequence of operation. Means for what kind of fault we need to check the system is whether coordinated or not. So here there are the types of fault: three-phase line to ground fault, line to line fault, and double line to ground fault option. So for line to ground fault, let's select with line to ground fault in ETAP. Now here with the help of this fault insertion in this ETAP, we can check this sequence of operation. Means if this fault occurs in any particular network, then the sequential operation will be the similar way which we have done. Now here you can see the operation that is 1 here and 3 is here. It means 3, which indicates the phase fault condition. Phase fault, you can see. Sorry, 3 operates in instantaneous protection. That is the fault current which goes beyond the 50 ampere, 53 ampere. That's why the instantaneous protection, which we have set for 4000, operate first, and then the ground fault protection operates here. You can see. So for this, there are 2 provisions we need to adopt. The first one is we have a provision that we can turn off this protection. It's extremely downstream network. We can turn off this protection as this is the extreme downstream network. We can turn off this protection, and simply with the help of this, the protection will be achieved with the short circuit condition. Listen, yeah, the protection will be achieved with the short circuit condition also. So this is an over benefit protection. If we can add up, if we want to add up, we can. But we suggest, normally what we suggest is to disable this protection, because many times malfunctioning of this protection is observed in practical stage. So what we recommended is to disable this protection for instantaneous protection for this LVCB trip unit. Now you can see the instantaneous protection for ground fault, time margin of 0.3. Okay. Now you can see the operation did operate first phase. It means if ground fault occurs in the system, then it will create in 80 milliseconds depending on the time delay of circuit breaker. But if ground fault protection feature does not operate within this simulated time, then there will be a overcurrent in single phase, we can say. So due to this overcurrent, the phase fault protection will operate in 140 milliseconds. And then after the ground fault protection will operate of the circuit breaker. this circuit breaker in a 200 milliseconds, or the desired time delay which we have set. Now for certain ground faults exist in the system, that is REF protection, restricted earth fault protection, and standby earth fault protection. So as the term this one of our attendees mentioned, that earth fault protection. So I will also mention that there are certain another protections for earth fault, that is REF and SEF protection. REF means restricted earth fault protection, which is used for the unit protection of transformer. And SEF means a standby earth fault protection, that is very last line of defense for earth fault protection, that if any protective relay in between the path fails to operate, then at last standby earth fault protection will operate, and it will protect the system to get severe damage.
Right. There's
Anything?
a question from Tyagarajan.
Yes.
Can the ETAP model snapshot showed in today's session shared along with the PPT?
Sorry.
Can the ETAP model snapshot showed in today's session will be shared along with the PPT?
Okay, sure. I will take a snapshot of this SLD single line diagram which we have modeled for this, and we can share with them.
Okay, thanks. Done. Any more queries, guys? Good. I think, guys, please give your valuable feedback. That would help us in understanding you more better way, and to reach you people also. As many of the people actually asked about the training and the content we give, I'll take 2 minutes of time to explain what we do exactly. So, as already mentioned, that HIW is a training institute who train only the electrical engineers. We give training completely of 2 months duration on electrical system design, along with the softwares of ETAP, E3, Revit, PVSys, Google SketchUp, Dialux, as well as AutoCAD. Okay, and this training would be 3 to 4 hours or 2 to 3 hours based upon the content delivery. We are into offline as well as online from this year, and we have a batch starting on 28th January. So you could also kindly consult us regarding, and our numbers have been mentioned here. Okay. So please reach us if you have many queries, and you have any other things regarding the ETAP session that we have conducted. You can reach us, and we will surely reply you based upon your query, and reaching Kashish on this also. Yes, Kashish?
Yes, yes, sure. Whenever if there any query raised, just forward it to me. I will sure. I will.
Yeah, you will get a reply from our team, or as well from Kashish, or we'll
Yeah,
forward it to Kashish, and you'll also get the same thing from us. Okay.
yeah, sure. If
Please contact whenever you have any queries and all. So that's all for today. Kashish, you want to add something else?
I will add that if this is the vast field, and if any of
I
our
agree.
upcoming engineers are interested in this, please contact HIEE, as they are having good team for this. So you can take a benefit of this team and take advantage for your career.
Thank you so much, Kashish. And it was wonderful session, I would say, because maybe the freshers who are not at all aware of what is ETAP has got
Yeah.
very good, clear understanding of how ETAP is helping in understanding the coordination and all. And I really feel that it was tough for you to combine all the package in one single session of 2 hours to help them understand in a better way. And that was a splendid try, I would say. Thank
Yeah,
you so much. It was very valid
yeah,
session.
actually, this very vast field and lot more I wanted to say, but due to limited time, just only cover some of the basic topics. But anyhow, we will try to get some more studies. Like, yes, for this relay coordination, there are certain studies which we also need to perform. That is load flow and short circuit. So with this,
Sure,
they
sure.
can they
We
can
will
have a
also have
better
another
idea. They can
session.
have a better idea for this relay coordination also.
Of course. Thank you,
Yeah,
Kashish.
thank
There's a question from Rahul. Is there any online training? Yes, Rahul, we have an online batch starting on 28th also. You can please contact the numbers given above. That would help you to understand in a better way. Any more queries, guys? Any training please provide on PSCAD, PSSC, and PLSF? No, sorry, Tyagarajan, we don't provide the training on PSCAD and all. You can look into our website. Our website is www.hiee.in and get more information. And you can also come to us anytime. We are available. Thank you so much, and thank you so much, Kashish, for your valuable time. So I think
thank you
we
for
don't have
inviting
any,
me.
yeah,
Thank you
we
for
don't have
inviting me.
any technical queries also, Kashish. So we'll end the session, I feel. Okay, where is the
Yeah, yeah,
institution
sure,
located?
sure, sure.
Yeah,
Hope
it's located at Hyderabad, guys, in SR Nagar. Okay, please, you can reach us. The location is on maps. Thank you. Right. Thank you, Kashish, and thank you all the team for making this session wonderful. And I always wish you a happy new year again and have a wonderful year ahead. Thank you.
thank you.